Good morning, Fancy Meat Computers. How's everybody doing on this beautiful Wednesday morning? The sun is shining, the birds are singing. It's a beautiful, beautiful fall day. So, let me just check the Avenue announcements very briefly to see if Mark didn't put something up. I'm pretty sure that I didn't put anything up since yesterday, but, you know, one can never be sure about these things. Oh! There we go. Yes, he did. Thank you, Mark, if you're listening. So, for those of you who may be under the despotic tyranny of one JC3 at the moment, we were talking about these Haskell resources that I gave to my third year class, and you guys expressed some interest in them, so here you go. I think these are some pretty good resources for learning Haskell, which, you know, Haskell is a very fun and cool language, and if I'm still teaching 3MI3 by the time you get there, then you'll need it. So, but coming to like a practical understanding of Haskell, I can't imagine that would hurt your chances in your discrete math courses that are coming up. But ooh, just got out marks back for calc. Uh-oh. Despairing over calculus right now. Ooh. What was the class average? Did they release the class average? Gross. Starting to warm up to Haskell. Yeah, Haskell is like, it takes some getting used to, for sure. And I guess the idea 68. Oh, that's not so bad. 68 isn't so bad. Be glad that the be glad that the class average isn't a flunk, because that sometimes happens. So I just want to say one brief thing for all of you guys who are in first year. You may need to adjust your expectations for what marks you get on things versus coming out of high school, because high schools don't really mark people very, like, harshly anymore, you know. It's been the position of people in secondary school that, you know, the marks coming out of high school are not terribly meaningful and haven't been for some time. But, you know, the standard used to be that a B means you're meeting expectations, a C means that you're below expectations, a D is that you're well below expectations and you need to do something about it, and F is obviously you are not meeting expectations at all, and A is you are exceeding expectations. So marks that, you know, the sort of exceeding expectations category typically starts at an 80%. So an overall mark on a calculus midterm of 68% is actually a lot better than some of them that I've heard. So, like, I'll often have tests that are in that vicinity. So, yeah, this is just the way that secondary school is, and you need to adjust your expectations accordingly. The main thing is not to have a panic attack because you're no longer a 99% student, you know? Like, in high school, you might have been, you know, you might have only been satisfied with a mark that was above, like, 95%. But here, your goal should be to, your goal should probably be north of 80% if you were in the former category. But, you know, and if you're in the medical faculty, you know, good luck, because they expect extremely high entrance averages to get into med school. But, yeah. Unfortunately, y'all gotta start thinking C's get degrees. This is very true. Personally, I was a B student. So, it's telling us... no, it's still on the old microphone. Let me check the other one quickly. Nope. Still having driver issues, unfortunately. What if you didn't even get a C? Then you should study harder. Yeah. So, yeah, also, this is only going to get worse as you go on, right? Like, right now, like, your first or possibly second calculus midterm of your first or second calculus class is, like, just wait till you start doing, like, differential equations and like, multivariate calculus. You know, things get really complicated really quickly. But anyway, yeah. Is Haskell used anywhere in industry? I just wanted to address that question before we moved on, because yes. Yes. So Facebook. You may be familiar with this website that has been gaining a lot of popularity lately, called Facebook, for their spam filtering algorithm. That's been written in Haskell. If you look at these, like, the big tech giants, you'll find that like, they're not necessarily using Haskell, but they will. A lot of them will use functional paradigm programming languages, but like it's not usually the surface level stuff. It's like really deep level stuff that's inside of the regular algorithms. It's like functional programming is definitely like a specialized subdiscipline of programming that doesn't see a whole lot of use. Fortunately, learning how to program functionally will improve your programming skills in general by quite a bit. So it's useful to learn functional programming even if you, aren't explicitly employed doing functional programming. And let's be fair, if you're employed doing functional programming, it's probably because you have at least a master's degree. Or equivalent industry experience. But yeah, learning Haskell has definitely made you better at implementing recursion. Yes. Oh, sorry. Tanya only knows MySpace. Yeah. Yeah. So yeah, it's kind of like how learning a language, like learning a new spoken language, will make you better at the language you already speak. Because you're just paying more attention to the way that languages are put together. But anyway, so we need to get motoring with this material. So we're going to have a fairly hefty chunk of today's lesson be about recursion. So those of you who have been programming in Haskell will have an advantage in this naturally. Our higher level CS courses, Omega level difficulty like the math ones. Ask Mark. I will redirect you to Mark. So please think of the TAs as being like they don't just have to answer questions about the course material. You can also ask your question. You can also ask the TAs questions. What's it like being in your year of this program? And I'm sure they'd be happy to talk to you about that. Yes. So, anyway, so we were talking about scoping. Just a quick recap of scoping. Global variables are things that are declared inside of the Python script's context and not inside any particular function. A variable that is declared inside of a function is considered local to that function and is not accessible outside of that function. We've seen this multiple times in various examples. If you want to specifically declare a global variable for use inside of a function, you have to use the global keyword. The thing, like if you were to just use in this case, in this example, the variable res, if you were to use res without the global keyword, it would create a new instance of the variable res that was local to the function. So when you try to access res, like in this example, if we do something with this variable, have the factorial function run, if we didn't have this global moniker applied, when we printed res, we would get 1, not the result, because the local version of res would be deleted when the function ends. And we would refer back to the pre-existing global version. So that's all well and good. So global just kind of pops it in from the global context into the local context. It's like snakes and ladders. By declaring a variable global, you are providing it a ladder into your function, and also a snake down out of your function. I don't know. Is the snakes and ladders analogy useful? Because if it is, I'll continue to use it. Are board game analogies in general useful? Because if so, I'll continue to use them. So the interesting thing, and one of the reasons that we try to avoid global variables, is that global variables tend to have unintended side effects. So consider this particular way of doing the factorial function. If we are, like, the idea with this guy is we have the result that is, we're trying to store the result of the function in a global variable. You'll notice that this function doesn't have a return value. Res is what we call an implicit return value. So we don't have an explicit return statement, but this global variable, the data that's stored in it once the function is fished, that is our result. I usually associate snakes and ladders with losing progress easily. Yes. Actually, fun fact about the game Snakes and Ladders. Did you know that it's actually the reason it's Snakes and Ladders is because of Christian imagery? Because you have the vision of the ladder into heaven in the Old Testament or New Testament, one of the testaments, and then the snake is obviously the snake from the Garden of Eden. Anyway, just a fun fact about snakes and ladders. But anyway, so the problem that we're going to run into here is that if we run this guy multiple times without resetting it, without remembering to reset it, we're going to get incorrect results. Because, basically the way that you want to set up a function is so that you don't require anything except the call of the function itself in order to compute the correct value. So when you're initializing something, since it has to be initialized the same way each time, you put that in the function. And with, acquiring results, the return statement permits you the same gosh darned thing. Question. So we can use global variables as an alternative of return statements. Bad alternative. Yes, you can also use them as an alternative for arguments. Right? A global variable is both an argument and a return value implicitly. And, they store their values between different executions of the function. Actually, the main thing that they're useful for is storing their values between different executions of the function. I'm going to do an example a little later on today or possibly on Friday when we're doing recursion of using a global variable to count the number of times a recursive function is called. But we'll see that when we get to it. Got to keep moving. Yes. So, software design principles. Let's talk software design. Modularity and decomposition of a program are extremely important principles. So whenever you're thinking programming, you should be thinking in Lego, right? You should be thinking, this is a little block, it has a specific purpose, and I click it into the other blocks to have it fill its purpose. Programs, ideally, work in exactly the same manner. You should have a known input, you should have a known set of inputs, you should have a known output, you should have known properties of these, of the output with respect to the inputs. What this does with our brains is it allows us to ignore the implementation details of the functions themselves, which is an extremely, I cannot even begin to describe how important it is to be able to ignore the contents of functions. Think about, this thing, right? This is like a little, 1 by 3 by 3 Rubik's Cube, which I, fiddle with during lectures sometimes. I don't have to know how it works. All I have to know is that if I turn the pieces turn. I don't have to know anything about the internal mechanics of this thing in order to operate it. This is the situation you want to be in with respect to programming. So a good program is well modularized, This means that the modules are reasonably self-contained, they have a clear purpose, and they can be reused. So when we talk about all of this, what we are actually talking about is the principle of abstraction. Abstraction is a super, super, super important thing with respect to the way that human beings think. So it's like abstraction is an extremely useful tool of the human mind as well as a tool in programming. A component function of a program can be used without knowing how it achieves its goal. So think about this, right? Human beings, at all points in our daily life, are operating inside of a world of abstractions. I'm not... Oh. No, I'm not a cuber, but my wife is, actually. She has the speed cube. She's very good at it. No, I've never actually been able to solve a Rubik's Cube. So think about something like a car, right? When you are sitting in a car driving it, you're not thinking about the carburetor, you're not thinking about the spark plugs. Generally speaking, you only think about the internal components of a car when one of them has gone wrong or needs maintenance. This is correct, because if you had to think about every internal component of a car while and before driving that car, you would not be able to drive the car, right? It would be cognitive overload. Your brain would just explode from all of the detail, especially with cars these days, because they're getting very complicated with all of the electronics that they're putting in them now. You know, arguably, in the 1920s, you could fully understand your engine at the same time as driving one. And it's useful to understand information about your engine, because that allows you to diagnose problems with, like, without, you know, by listening to noises and stuff like that. But yeah, as one of your classmates has just pointed out, you can watch this stream on YouTube without knowing anything about how YouTube is delivering this stream to you. And let me tell you, like half of the effort ever put together by human beings has gone into you being able to watch this stupid stream, right? Yeah. So, you know, so this level of abstraction is absolutely necessary in order to be able to operate software particularly and specifically. This is kind of like the... this is the arrogant brag of CS as a discipline, but software is actually the most complicated thing that human beings have ever developed, aside from having evolved their own brains. Right? Computer software is the most complicated thing. Right? So in order to deal with the most complicated thing, you need to be able to rely on your abstractions. So, and, you know, we're also going to have classes eventually as a means of abstraction, but for the moment we're talking about functions. Large programs will have many functions. Many of the functions that a large program in an object-oriented language will have are packaged up with data. That's what a class is. But, you know, functions are what we're talking about right now. Each function should be relatively small and designed to do only one thing. For example, Twitter. In Twitter, storing a new tweet to the database is one function. Liking a tweet, one function. Deleting a tweet, one function. Each button is a function, right? Yeah. Yes. Trust me, once you get into being a software person professionally, if that's your goal, you will at times rue the day that you decided to get into software, because software is so damn complicated. Believe me, that's not an ego thing, because you're like it would be an ego thing if you never had to actually write any software. Yeah, they should make a function to evaluate a tweet to find out if it's worth adding to the database. I mean, that's kind of what all the censorship business has been, right? That's actually present in their mind, but yeah, enough said about that. Incidentally, the thing I always tell people about Twitter is Twitter is just a database. It's the people on Twitter that are scary, not Twitter itself. Anyway, so so it's important for functions to be for us to be able to think about them abstractly. So it's also important for us to know things about them, right? So typically, we document our code. We document our functions. Excuse me. What the documentation is ideally supposed to provide is it's supposed to provide a written description of a function which tells a potential user everything they need to know about the function without having to know the specific implementation details. So you need to know what the inputs are supposed to be, what the output is if the inputs are correct, and, you know, any other conditions that are required in order for the function to work. This is what you would include in documentation, typically. In Python, we have a particular way of going about this called a docstring. Which we'll see on the next two slides. But yes, so we need two things. Assumptions, requirements, preconditions, what conditions the input must satisfy for the function to work correctly, and guarantees/post conditions, what conditions the output will satisfy so long as the input conditions were satisfied. Now, you may have heard of this phrase before. Garbage in, garbage out. This is the law of computation. If you put garbage in, you will get garbage out. So what defines garbage? It's garbage if it's not following the assumptions that are explicit and implicit in the design of the program. So the idea of documentation is that there should be no implicit requirements after you have finished documentation, right? Everything that the function needs to operate should be stated inside of the documentation. So, for example, our make_change function. The way that you write a docstring in Python is on the line after the function declaration, you open 3 quotes, and then you write stuff, and then you close with 3 quotes. So for the make_change function itself, our documentation reads, assume target is an integer, and that coins is a sequence of integers in descending order. Returns a dictionary with a key for each entry in coins and corresponding int for the number of coins of that denomination. It describes what the inputs are. It describes what we expect from our inputs. It describes what the output should be. Now, if you're working in better languages than Python, many of these you can turn these requirements into actual explicit requirements of the language that will prevent programs from compiling if these are not met. In some languages, you can even enforce things like coins as a sequence of ints in descending order. You can even enforce things like orderedness over things like lists. So Python, I don't like Python. You may have gotten the impression that I don't like Python over the course of this course. I don't like it because it doesn't really defend its own abstractions. Like, it doesn't really... I don't consider it a very safe language because it doesn't require you to actually stick to the data types in particular of the things that are being passed around. Python's attitude towards data types is basically like, well, you can figure it out, and we'll just work around you, and that's bad. You know? That's not the best way of going about it. But anyway. So this is what a docstring looks like. So the interesting thing about docstrings is that you can use the help function, and whatever you have written as the docstring will be barfed up by the help function if anybody calls help on your function. So this is like Python's inbuilt documentation system, which is kind of cool. Aren't classes just a collection of functions corresponding to the same objects? Well, I would say that a class is a collection of functions and variables. So if you take a bunch of variables and a bunch of functions that relate to them, and you package them up as one entity, that's what a class is, and that's also what an object is. But we're going to get to object-oriented, in a few weeks. Is Java greater than Python? Yeah, I'd say so. Again, I'm not a huge fan of Python, but I'm also not a CPP guy. Most of like my actual, when I'm actually working on like pleasure projects, I'm usually doing a video game, which means I'm usually doing C# because I use the Unity engine. But C++ is also, it's okay. C is like C++ aren't exactly safe either. But yeah. In theory, Python is easy to learn because you don't have to worry about all these typing details. I use Fortran because I'm retro like that. Ho ho! A scholar of ancient languages, I see. So, anyway, talking about recursion. So, isn't C# Microsoft's fake Java? Yeah, that's a fair description. That's a fair description. I did my thesis work in Haskell. Yeah. Yeah, Rust has been gaining a lot of popularity lately. So anyway, factorial recursively. So we've talked about how to define factorial before, right? We've done iterative solutions to factorial, which means we've done factorial using a loop. But we haven't done factorial in the language that factorial is natively defined. That is to say, we haven't done factorial recursively. So, if you, I'm just gonna, what is this, topic 5? Oh, gosh. What horrible, there, that's better. Okay. So, comment. There we go. There we go. So, this is what we call an inductive definition. Notice how we're using factorial to define factorial. Under normal circumstances, that is to say, in any course other than a CS course, or possibly math courses some of the time, discrete math courses more particularly use this type of formulation. This would be called circular reasoning, right? This would be a circular argument because, you don't use the word fish to define what a fish is, but we are here using factorial to define what factorial is. But this is absolutely correct. If you take the factorial of 5, that is equal to 5 times the factorial of 4. This is actually correct. So, we can actually implement this in Python fairly straightforwardly. fact. It's a fact. N. If n is equal to 0, return 1. Else, if, or elif, n is greater than 0, return n times factorial of n minus 1. There we go. Yes. Linux shortcuts. We are doing recursive type stuff in linear algebra right now with determinants. Yeah, determinants is a recursively defined algorithm as well. I've actually had, in the past, I've done recursive determinants as a test question. Do an implementation of determinants recursively. I've had that as like an exam question before. So, just to see what's going on here, you know what? I'm going to do this in Python Tutor. I always like remember Python Tutor after I've typed it out. So, factorial of 5. Visualize execution. Get out of here, you. There we go. So, as we go through here, we call factorial with n is equal to 5. We then skip down to this return statement, right? In order to calculate this return statement, we need to call factorial with n minus 1. N minus 1 is 4, so we open up a new instance of the factorial function with n is equal to 4. We then go through again, that calculating factorial of n, factorial of 4 requires us calculating factorial of 3. Factorial of 3 requires calculating factorial of 2, etc., etc., until we reach 0. The factorial of 0 is 1, so we get a return value of 1. That return value is passed up through here. We can now complete this expression, right? Now that we can complete this expression with n is equal to 1, we get a return value of 1. We can pass that up to the instance of the function where we are calculating n is equal to 2. So the return value is now, we then calculate the return value with n equal to 2, pass that up to n equals 3, return value is now 6, pass that up, 24, pass that up, 128. 128 is your final answer. So there you go. So this is not tail recursion. Tail recursion requires you to have a data structure where you break off the head and then recurse on the tail. This is a numeric recursion. This makes me appreciate Haskell's pattern matching even more. Yes, absolutely. Like, really, for those of you who aren't in 1JC3, Haskell doesn't even have loops. Not in the proper sense. It uses recursion for literally everything. So in order to program in Haskell, you have to know loops. Or you have to know recursion. There's no other way to program in Haskell. So is this as efficient as a loop? No. It's not as efficient as a loop because it has to introduce more stack frames, right? There's a certain amount of overhead with each function call. So generally speaking, this type of recursion isn't more efficient. In a language like Haskell, which has been optimized for recursion, it is more efficient. But in Python, this is not as efficient a way of going about things. But it's not about efficiency. There are problems that you can solve with recursion much more easily than you can solve with loops. So this is like a secondary strategy for problem solving. Is it true that lambda calculus is based on recursion? No. It's not actually true. I can answer this problem. I can answer that question exactly now that I've taught this course. Lambda calculus is not based on recursion, but recursion is it's easy to implement recursion in lambda calculus. You would have the fixed point combinator is a simple lambda expression which allows you to perform recursion in lambda calculus very easily. Lambda calculus itself is not like, it's not inherently recursive, but you can construct recursion very easily in it. It's kind of like saying, you know, it's like saying you can make cheese out of milk easily, but that doesn't make milk cheese, right? We can still distinguish milk from cheese, even though you can make cheese from it very easily. So, is it a general rule that recursion is less space efficient but more time efficient? No, as we're going to see. It depends on how you're doing it. So in general, when we have a recursive algorithm, we break it up into two or more cases. The first case is, in this instance, the first case is what we call the base case. The base case is the case that does not contain what we call the recursive call. So if we take a look at the structure of the algorithm, this here is a calling of the factorial function within the factorial function. This is a recursive call. We are recursing. Basically, any function that calls itself is recursive. That's the definition of recursion. Recursion is actually a very general term, and you have a number of different types of recursion. But, we're talking about recursion in the most general sense possible. So, the case that does not include the recursive call is called the base case, and it borrows this language from induction. I don't know. Here's a question. Does anybody know what induction is? Does anyone know what induction is? I want to make sure I understand this. So every recursive call creates a new stack frame, which is space inefficient. Well, it's kind of space and time inefficient. It's inefficient compared to a loop, right? Which is just execution instructions. So, yeah, you have to pay an overhead cost every time you create a new function call, right? So that overhead cost is going to be more expensive than any savings you get for something this simple. If it's something else, the more complicated, in different circumstances, where the function overhead is minimized, it's small in comparison to the amount of processing you're doing, you can make the argument that it's negligible, the function call overhead. But yeah, there should be a somewhat option. I feel it in my soul. So, oh my gosh. All right, I guess this is my life now. So, induction. So, induction is a style of mathematical proof, which you're not going to see until at least you take a discrete math course. More likely, you won't see it until second year. So I'll give you just a rough sketch of it right now. So here's how induction works. You have a base case, and you have something that's true about that base case. You then prove that for any n, this must be true of n plus 1. You have now proven that whatever you're proving has to be true for everything, because n includes the case where n is equal to 0, right? So basically, if something is true for 0 and it's true for it being true for n means it's true for n plus 1. That means that if it's true for 0, that means it's true for 1. If it's true for 1, that means it's true for 2. If it's true for 2, that means it's true for 3, etc., 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 all the way to infinity. So it's a very, very powerful mechanism for proving, you can prove predicates over the natural numbers using induction. That's like the preferred way of doing it. But yeah. So in this case, the analogy to recursion, like we have this base case, right? So it's kind of like doing that in reverse, right? For induction, you're trying to prove that you're trying to prove something true for n plus 1 given n. In this case, we are calculating n given a definition for n minus 1. Yeah. In India, we learned induction in grade 12. Well, it sounds like you have a better math program in India than we do in Canada. Well, I shouldn't say that. When I was but a lad in high school myself, I took a course which no longer exists in the high school system called Geometry and Discrete Math. And in that course, we did mathematical proof in grade 12 of high school. Only about 8 people in the high school took it, including myself. I was one of those like mad students who didn't take a spare, and I took 3 science classes, 3 math classes, English, which you had to take, and then visual arts. But yeah, I did induction in high school as well, and I'm very disappointed that the mathematical education in Ontario is slipping to the degree that people don't hear about this sort of thing anymore. Unless anybody can correct me on that. If anybody listening in the chat learned about induction in high school, I'll eat my hat. I'll eat my words. Assuming you were in Ontario. But yeah. Is recursion and induction the same thing? No, they're not the same thing, but they're related. Recursion is the preferred method of solving inductively defined problems. Yeah. Cool. Public curriculum, it's just in special programs. Okay. Well, I don't have a hat with me, so you'll have to wait. So, this is just explicating like what the actual values are as you run the program, but we did that in Python tutors, so that's fine. Every time we recurse, the interpreter creates a new scope for the variables of the function. This is true. So the consequence of that, basically, and this comes out really clear in Python tutor, if I had some variable here, x is equal to 3, right? Each one of these calls to factorial will have its own separate instance of x, right? So, x, while we're in this function, we'll be using this version of x and not that one, basically. You always refer to the most local context. Yeah, so induction is like the question and recursion is the answer. Yeah, that's an okay way of framing it. Like certainly in the context of like a math problem, I would give you, you would get a function defined inductively, and then you would be expected to perform, like you would be expected to translate it into a recursive function. So in your sense, yeah, but I would say it's like induction isn't really it's not really a question in that sense. It's more like a definition, It's a way of defining things mathematically. But yeah. So, recursion is a natural technique for solving problems with an inductive structure. But depending on the structure of the problem, recursion can be inefficient. So we're going to... We'll implement Fibonacci. Can I show you an inductive function definition? Yeah, ta-da! Here it is. This is an inductive function definition right here. This is it. This is an inductive function, my friends. So Fibonacci numbers, right? Most people should be familiar with the Fibonacci numbers. Although I think you guys are getting too young now to remember the Dan Brown, like the... what's it called? Not Angels and Demons, and not the most recent one. The Da Vinci Code. If you remember the Da Vinci Code, that the Fibonacci sequence featured prominently and entered pop culture's orbit for a period of time. So the Fibonacci numbers, basically the definition of the Fibonacci sequence is that every number in the sequence is the sum of the two previous sequences, or sum of the two previous numbers, and the first two are 1. Although it's interesting, you can actually define Fibonacci number 0 as 0 and 1 as 1, and it still works. But it just offsets it by 1. So, fib n. If n is equal to 1 or n is equal to 0, then we return 1. Else, if n is greater than 1, return fib n minus 1 plus fib n minus 2. There we go. So, I'm going to do this one in Terminal rather than in Python Tutor. So, print fib at 10, let's say. And yeah, I know, I'm just about out of time. There we go. Python 3, topic 5.py. This function is deceptively simple. Yeah, we're going to make it more complicated, though. Oh, I got to delete this nonsense. Yeah, that's the thing, right? Is like, with recursive definitions of functions, you can actually get some, like, pretty, like, readable stuff out of it, right? Like, this looks very similar to the inductive definition. This is part of the strength of recursion. So this is good. Fib 10. So let's try a, so I'm gonna do a Linux thing. I'm gonna use the time function to be able to tell us how long the computer takes to calculate the number, right? So here's the problem with this approach, right? So it takes us 0.004 seconds of system time to calculate 10. How about, save that, how about 11? Oh, it disappeared on me. All right. I think I have to hit like the 30s before this. Yeah. Okay. I'm going to skip a few. See how 30 takes it. Yeah, now we're starting to hit something. So, 30 takes us, well, we'll just go with real time. About 0.2 seconds. 31. 0.3 seconds. 32. Oh gosh, come on. Work with me, computer. There we go. There we go. So you can see for each one that I increase here, I'm starting to run into noticeably long times. If I skip a few, say I skip right to 40, it's taking a long time to calculate this. What kind of rounding do the poles have? Yeah, that's kind of suspicious, isn't it? How do you come up with the iterative case? It should be obvious from the structure of the problem. Oh, okay. I'm out of time. But you can see that that takes way too long. And next time in class, we'll see how to fix that. Yeah. Yeah. And Neil has given us the answer. Yeah, that's what we're going to be doing next time in class, is storing intermediate results. Basically, the problem here is that it's having to recalculate a whole lot of numbers to calculate numbers, and that's not efficient. So we're going to produce a more efficient algorithm next time in class, and we're going to do a better version of this. So to answer. What is the time complexity? Currently, the time complexity of this algorithm is sitting at big O of 2 to the n, which is why it's blowing up like this. So can we use tail efficient to make this recursion efficient? Tail recursion to make this efficient? No, we're going to use a technique called memoization, which is actually more closely related to dynamic programming. Tail recursion is kind of like a matroid-type solution, whereas memoization is a dynamic algorithm-type solution. Yeah. Yeah. Any other questions? Any further questions? So we'll have an aux function. I don't know what an aux function, what you mean by that in this context. I know that probably stands for auxiliary. How much more efficient is Haskell in recursion than Python? I don't know. Here's what you could do. You could implement the same function in both languages, call it on the same number, something sufficiently large that you'll get meaningful results, like this stupid implementation of Fibonacci. And you could see how much more efficient Haskell is. I believe that Haskell would memoize it by default. I believe that Haskell will memoize it without you having to actually explicitly set that up. Because Haskell does this interesting thing where whenever it calculates the results of a function, it traces through your entire program and replaces any call with those parameters with the calculated result. I don't know if that would fix this implementation of Fibonacci or not, but it might. Yeah. Is Linux hard to get used to when you switch? I want to switch, but I don't want it to compromise your schoolwork. So with respect to Linux, definitely if you want to get Linux if you want to get your own installation of Linux, I would recommend buying like the cheapest laptop in existence that still has its bootloader unlocked. Not a tablet, because you need an unlocked bootloader, but just buy like a stupid little Acer, like a $300 Acer or something, and load Linux up on that. Like that'll be more than enough horsepower for anything that you need to do with it for schoolwork, for programming, because generally speaking, the programming that you have to do does not require a huge amount of horsepower. Yeah, and then you can still have your Windows laptop for all of the Windows stuff that you need for your coursework, and you can have Linux as an alternative. The other alternative to that would be dual booting, but I only recommend setting up a dual boot on a system that is completely factory new, because the thing about dual booting is that you have to take like a large chunk of your hard disk and partition it off for a Linux partition, and if there's any data on that whatsoever, it'll get wiped. And if you have if you have a laptop that you have any data on at all, it's likely that you'll lose data by partitioning your hard drive. So I just don't recommend it unless you have literally just opened the box on the laptop. I don't recommend doing a dual boot system. But yeah. If you use your computer every day, you'll get used to Linux in no time, especially if you start out with using beginner-friendly things. Yeah, like I would recommend something like Ubuntu or Mint, which are, very user-friendly distributions of Linux. If you're doing this to a brand spanking new laptop, you can probably expect some driver issues for at least a year, possibly longer. If you're having issues with your drivers, I would recommend taking your laptop to someone who really knows Linux well. iPop OS. That's cool. Yeah, you can also try with a virtual machine to start with. Like you can probably do everything that you want with Linux inside of like frankly, Windows Subsystem for Linux isn't terrible. It'll get the job done. Would I recommend learning from open source? Open source is that's like a style of licensing. I'm not sure what you would learn from it aside from the fact that projects that have open licensing tend to be longer lived. A company will shut down a proprietary piece of software when it's no longer profitable to maintain. Actually, what a lot of them have been doing lately has been like when they're no longer profitable, they just kind of release them open source. Some companies are doing that now, which basically just means releasing the source code, and so anybody can have the software for free. I'm not sure what you can learn from that with respect to programming. You might be able to learn something from that, by how internet economies work, if that makes sense. Your software, our software, comrade. Yes. I don't know enough Russian to be able to say that in Russian, unfortunately. It wouldn't be difficult, but let's see. That's longer than I expected. Karl Marx is rolling over in his grave. Let's see. Nasha Tovarish Programnomi? No, Programnomu. I always get Y mixed up. Obesp Echenil. Yeah. There you go. Am I Russian? No, I've been learning it the last couple of over the last like couple of months I've been rather than playing some stupid phone game, I've been like doing Russian language practice. So you can tell my level of it as how fluently I was able to pronounce that. But it's a lot of fun. Basically, I was playing Fez, and I noticed that I had become fluent in Fez glyphs. So I was like, you know, is Russian really that much harder than becoming fluent in Fez glyphs? What phone games do I play? I don't really play any at the moment. I'm just doing the Russian language practice thing with Duolingo. I like it. It's good. Except with Russian, it doesn't really give you any grammar lessons. So, you know, you have to go to other sources to learn like why there are no articles and stuff like that. Das Vidanya, Professor. Nyanada? Would that be an appropriate response? No, it's Das Vidanya is thank you. And it's frick. I was just doing this too. Spasiba? I don't know. If you've been wanting to learn Japanese, then there's never been a better time to learn it, because you can literally learn it while pooping. That's what I've been doing with Russian. Oh, yeah, Das Vidanya. Yeah, I'm... Yeah. Do I know what the labs in labs for 1xC3 actually are? Yes, I wrote them, so I have a pretty good idea of what they are. All right, I'm going to log off here. Take her easy, folks.